This is Garis MPC, that's Maths, Physics, Computing. That is 130 plus Masters and PhD level courses in pure mathematics and mathematical physics. This is course number 4, so MPC 4 on linear algebra, junior and senior level course. This is chapter or lecture 2 on the theme of linear algebra, and this is session D. From the previous session we had two systems, and the first was denoted by 1 asterisk, and that was a set of m linear equations, and the double asterisk was the set of m homogeneous equations. And the difference between these two, in the non-homogeneous case, this one, at least one of the b's, the constants of the equations, is non-zero, and in the homogeneous case, the 2 asterisk case, all the constants of the equations, all the b's were 0. Okay. Now there's an interesting relationship between these two sets of equations, these two systems of equations, and we'll prove it. Typically in the Schaum series, theorems are presented in statement form only, usually, in section 1, which is the condensed theory, and the proofs of the theorems tends to occur in section 2, in the solved problems section. So in section 2, problem number 11 will actually prove this interesting relationship, which I'll be discussing the next few lines. Okay. So remember from last session, a particular solution of the non-homogeneous case is just an n-tuple that satisfies every equation in the system. To satisfy just means when you plug in the values, the components of your n-tuple, that is the solution. When you plug that into your equation, the left-hand side equals the right-hand side. Right. So, so let U here be a particular solution of your non-homogeneous system. So, so U will be an n-tuple here. So. So these U's here, they're just real numbers, right? So and you'll plug in. So you're here. Here's like the general form of the equations in your system, and we'll have m equations in n. So I ranges from 1 to n. So your U, the particular solution, will range from 1 to n. From 1 to n. So you have n variables, or n unknowns. Okay, and these b's here, they're the constants of your equation, and j ranges from 1 to m. So so you'll have this will be, if you have one equation per line, you'll have m lines, m equations. Okay, and this U here solves each line, each equation. So the U's, like in the form of an n-tuple here, that's a solution to your system, to your set of equations. All right. And it's a particular solution. You know, it's just one that works, and call it U, and it's a particular solution. So how do you go about finding the general solution that includes all possible cases, all possible solutions? Well, you go about by using the homogeneous equation, set of equations, the homogeneous system, where that was labelled in the previous session by a double asterisk, a double star here, and that's the system, the set of equations, where all the b's on the right hand side, all the constants of the equation, they're all zero. Okay, so they're all the same. So hence homogeneous, a homogeneous system. So you find all possible solutions of the homogeneous equation, and let them be W. So say you have a finite number of them. We'll say there are a total of T of them, and so one particular solution for the homogeneous system might be this one. Oh, wait a minute. I don't know. I may have made a mistake here. Maybe this should be. Yeah, I think this should be N. I think that should be N. Because there are N variables. Okay. So what are we listing here? These are particular solutions, each one, and let's say there are a total of T of them, and this n tuple, because solution to, you've got n unknowns, not m. So you put them in a set, and you call this set the set of all the particular solutions to your homogeneous system. So all the equations in your homogeneous system, all the right hand sides, they're all zero, right? By definition, that's what homogeneous system means. Okay. So let's say you have T particular solutions for the homogeneous case. Put them in a set and call it W, capital W, right? Now there's a theorem called Theorem 2.1, and we'll actually prove it. We'll only state it here. That's usual in section 1 on condensed theory. But we'll actually prove it as question 2.11 later in later session. But the general solution is it's of the form W plus little u. Now remember, I need to explain what that means. It's not so obvious, but it's general form. It's W plus little u, and I'll explain that in a minute. So reminder again, the little u, what is that? That's the particular solution to the non-homogeneous system here. It's these u solving this equation. So that's your u. And what's W again? By definition, remember, it's the set of all these particular solutions for the homogeneous equation, when all these b's here are zero, right? Now, okay. So what does this mean? Well, it's just a kind of shorthand, and it represents, in fact, t different sums. And in effect what it means is it's W1 plus U and W2, like this one. Oh, well, W. So the S particular solution of your homogeneous equation will be of this form. Okay, so you would have then WS plus U, and the last one would be WT plus U. In other words, this is shorthand for T sums, where W ranges over from 1 to T. So if you wrote this out, you'd have W1 plus U and W2 plus U and ... WT plus U. Okay? And that set of solutions, the set of solutions, in other words, the set of these sums, and you'll have T of them, is, by definition, the set of the solutions is called the general solution, or solution set, same thing. Okay? And we'll actually prove that in question 211, which is what I've just said. Right. Now, a remark that Lipschutz, the author of the text, makes is this W plus U sort of shorthand formula. It's more for theoretical interest because it doesn't really help much in the practical case of actually finding the general solution. To do that, you need a whole bunch of other techniques. So, what we'll start now, and it's a major theme not only of this chapter, but for quite a lot of the book, is the general approach on how to actually find a particular solution. And the key concept that gets used, like how do you solve the non-homogeneous system where at least one of your B's is non-zero? Well, the usual method is called by elimination. So for example, you have two equations, and you do some tricks, which I'll explain in a minute, and you probably did them in middle school. So you do some tricks, and as a result of that, you get rid of one of the variables. So you've now created an equation that's a bit shorter than the two originals. It's shorter by one variable. And you can keep doing that until you get until you've got an equation with just one variable in it equals some constant, and therefore you can solve for the variable. And then you can plug that solved value, you can plug that into the next longer one, and so on. If you don't follow what I'm saying right now, don't worry about it too much, because we'll go through this process many times. But the core idea is you take two equations, you do some tricks on them, and the result is you end up with an equation with one less variable in it, and you just keep doing that, one less, until you get a very simple equation with just one unknown in it, which you can then solve. So So here's a concrete, very simple, fairly simple. Concrete example of this process of elimination, getting rid of one of the variables, one of the unknowns. And you probably can remember well, I don't know, it depends on which country you're in. I think I learned as a kid, I think in the 8th grade. So it was called simultaneous equations, meaning you had two equations in two unknowns. Instead of x1, x2, just say x and y. X and y are unknowns, two variables, right? So what I'm talking about, this trick on how to eliminate one of the variables. So what is the trick? Well, here it is. Have a look at these. Now, here's the trick. If I multiply that line by 3, I'll get here 6x, right? And if I multiply this line all through by 2, I'll also get 6x here. So I've got I'll have a 6x here and a 6x here. So if I subtract these two lines that have, where this one's been multiplied by 3 and that one got multiplied by 2, so I'll get 6x and 6x, And if I subtract the two lines, I'll get 0x. So I've got rid of the x, and that's the trick, right? So generalizing a bit, what you do is you have a look at this first number here, and whatever it is, you multiply this equation by that number. And similarly, you have a look at this number, and you can multiply that equation by this number. So do both things. So you multiply this by 3, and you multiply this one by that, by 2. So you'll end up with 2 times 3 and 3 times 2, which are equal. 2 by 3 equals 3 by 2 equals 6. Then when you subtract the 2, you'll get 0x, 0 times x. So you've thrown out the x effectively. You have eliminated the x. This is a method of elimination. So that's what I'm basically saying here. One equation, one line, one equation. So this is equation 1, or line 1. Multiply that by 3, so you'll get this, right? Multiply this by 2, so you'll get this. So this new first line equation is just 1 dashed, and this new second line equation is 2 dashed. Now just subtract the 2, so 1 dash line, equation, 1 dash minus 2 dashed. So here's your first equation minus the second equation. Now you see there's no x term here, it's been eliminated. That's the whole point. And you've now got a very simple equation with just one unknown in it, which turns out to be, 9 minus, so it's 5y equals, so this times 3 minus this times 2, so 24 minus 14, so it's 10. And so 5y is 10, and then you can easily see that y has to be 2. Okay. Now if y is 2, you can plug the value of y equals 2 here, so you get 6. So 2x, take the 6 over, you get 2. So 2x is 2, so x is 1. Okay. So you've solved the equation. Now this is a very simple case, right? From middle school, 8th grade, or whenever you did it. But this idea of eliminating a variable by imagine an equation that's much longer, where you had many more variables or unknowns. Okay, and similarly the second line. But basically the technique's the same. You have a look at your first variable here, and whatever number that is, multiply the next equation by that number. And similarly, whatever number this is, multiply this equation by that number, and you'll get the new line 1 dashed and 2 dashed. The number here will be equal to the number here, and then you can subtract them. You'll get 0x, and you have eliminated your first variable. Okay, that process of elimination, that's a technique that we can use over and over again, and you progressively produce equations that get shorter and shorter and shorter as each time you go through this process. The number of variables in your equation goes down by at least 1. Okay, so this is by way of introduction, general feel for the method of elimination. Ciao.